Thanks for the invitation to address this esteemed audience today. I feel that I need to start this presentation with a couple of caveats. First of all, I am a data scientist. I know nothing about agriculture. Second of all, this is hardly going to be a scientific presentation. And that is because I am a man, third of all, man on a mission. And my current mission is, given the tremendous hype in this area of machine learning, that hardly a day goes by where the media don't report on artificial intelligence and machine learning. So we are living in very exciting times, but we have to put things into perspective, and that is my mission. And therefore, fourth of all, this presentation will be structured into two major parts. The first part has nothing to do with agricultural data analysis whatsoever, and the second part then has. So bear with me. And finally, a survey. Are there any hardcore machine learners in the audience? Deep learning enthusiasts? So you can kill me afterwards. Let me begin by looking at what's going on in machine learning these days, what has happened in the last 10 years, why is that such an important or popular topic nowadays, and that has to do with what is called the deep learning revolution. And basically what has happened 8 to 9 to 10 years ago is that 4 major technological trends have finally found together, have synced up, come together. These are the trends of big data. I do not have to explain that. That was the popular topic, say, up until 5 years ago. We live in the zettabyte age, and we have data everywhere. We are basically drowning in data. Second of all, affordable HPC refers to the fact that high-performance computing solutions have become cheap. Compared to 15, 20 years ago, you can get a lot of computational power for the buck. Third of all, because of the well-established and widespread use of the internet these days, open source software is commonly available, and everybody can find machine learning software and libraries out there on the web, can use them. Nobody has to start from scratch anymore. That, of course, boosts technological progress. And then the fourth trend is what we call deep learning systems. That has to do with machine learning. The other 3 components, or 3 trends here, are really not genuine machine learning trends. But taken together, these 4 developments have led to the dramatic progress in artificial intelligence we have seen over the past decade. And much of this was driven by neural networks, deep neural networks, which is a mathematical fantasy as to how the human brain operates. It's a mathematical model for something extraordinarily complex, which we still don't fully understand, but we can, let me go back one slide, come up with very reduced, very simplified mathematical ideas as to how a single neuron in a biological brain operates. And this is basically a very, very simple function. We imagine a neuron computes, and these very simple functions can be composed together into networks like these. We would call these neural networks. And this is a caricature of what is called a deep neural network. It is deep because the individual processing units in this architecture are arranged in layers, so we can recognize hierarchy here, and there's a couple of hierarchical levels, and that is what makes this network deep. It is a caricature because nowadays, if we look at what is done out there in the wild in companies like Google or Amazon, we're talking about hundreds of layers of these processing units and millions of neurons per layer, and that wouldn't fit on the slide, so you have to scale this by a factor of at least 100,000 to come close to what's happening out there right now. And computing machinery like that is of interest because I have to go back yet another slide. In these mathematical functions there are a couple of parameters which can be adjusted to the problem at hand. It works like that. Somebody provides you with data, and ideally with enriched data, with data for which you know what an individual data item signifies. For instance, with pictures of infected plant leaves, and you would have data of healthy plant leaves and infected plant leaves, and maybe you're just interested in the question, is a picture I have never seen before infected, does it show an infected or a healthy plant? In order to come up with such a decision automatically, you can train systems like that based on the data you have in a supervised manner. And the training process is that you feed your training data to this architecture, and up here a decision will be made. This is all really just mathematical computation, some encoding of the decision. And if the decision does not correspond to the answer you wanted to have, say you feed in a picture of a diseased plant and the network says healthy, then that was a mistake. And because in the training stage you do have this enriched metadata, this controlled data, it has made a mistake, you know that, and you can ask yourself, how would I have to adjust the parameters of this architecture such that the mistake would not have happened? If I had adjusted those parameters, how would I have to adjust the parameters in this layer of this architecture so that the mistake would not have happened? You propagate this error back through this network in order to correct the parameters which you can adjust. That is what we call machine learning. Like adjusting the parameters of mathematical models which are supposed to describe certain real-world phenomena or are supposed to do decision making. This is really, for those of you where it's a long time ago that you've done parameter adjustment, everybody in this room has done this in high school when you learn to fit polynomials to a couple of data ports. Right? And this is the same thing, slightly more complicated. Now, given that we have tremendous amounts of data nowadays, and that we have very powerful computers which can do the necessary computations that are necessary during training of these architectures, we have seen tremendous progress in, for instance, cognitive computing that pertains to text analysis, image understanding, speech recognition, robotics. And that is of practical interest. These are examples not from phytomedicine, but from human medicine. For instance, in medical diagnostics, where we are dealing with data like these are mammographic pictures, these are pictures of the retina of the human eye. If you suffer from certain diabetes conditions, that can be read off the retina of your eye. So in medicine, people analyze or diagnose these images. And there are a lot of images like this out there. And machines have been trained based on this data to come up with diagnostics. And it turns out that these machines, these basically neural network-based machines, can do this much more accurate and much more reliable than human experts. And it is observations like these that have led to the hype we are currently living through. Whenever I'm talking about the fact that machines can more reliably diagnose diseases than human medical experts can, people are offended, and rightly so, because it touches the very nature of who we are. How can this be? But indeed, this is not necessarily surprising. Imagine you were a human medical doctor and say, outrageously, let us assume, you were to diagnose 100 X-ray images a day. No radiologist does that. 100 is way too much, say probably like order of 20 or so. But if it was 100 a day, then it would be say 500 per week, 5,000 per year, and then in 40 years professional careers, 1 million images that a human medical doctor would see. These learning machines are trained with the order of 10 million and more example images. So from a purely statistical point of view, it's hardly a surprise that they are more sensitive to certain characteristics in those data than the humans. The miracle really is that the human brain can do it, even if during your studies at university you've seen only 20 or so examples. That is the miracle, the flexibility of the human brain to be able to learn to accomplish such tasks on just a very few examples. So, and therefore the question then is, well, if all of this is so, and what I've talked about so far is basically what you read in the newspapers every day, what you see on TV or in the social media, is deep learning therefore the tool to end all tools? Do you just have to, you know, hand me a hard drive of a couple of petabytes of data and then we'll solve all the analytics problems in PhenoRob? And now the man on the mission part starts. No. And again, this has nothing to do with agriculture, but it's fun anyway. What we can see here is a picture of a husky. It's kind of dog pulling sleds. And this picture has been classified by a deep neural network that was trained to analyze images showing animals, giraffes, elephants, dogs, cats, huskies. This neural network said that was a wolf. That's okay, isn't it? I mean, this husky is, among all the dog breeds, visually fairly close to wolves. But it was a mistake nevertheless. And Ribeiro and his colleagues tried to explain how this mistake came to be. Now, I have to take a poll. Those of you who know this example, please be quiet for 5 seconds. A poll. What do you think was the reason for this artificial intelligence system to classify this wolf, this husky, as a wolf? Was it the fangs, the snout, the ears, the eyes? What was it? In this image, it was these pixels that caused the classification as a wolf. How can that be? It turns out that in the massive amount of training data that was used to train this deep neural network to learn to recognize the content of images, they had many pictures of wolves, many pictures of dogs, but it turned out, in hindsight, that every single picture in the training data that did show a wolf also showed snow. And statistically, that is the obvious decision to make. If there is snow, then there is wolf. Nobody in this room would have used these parts of the image to come up with a class label for this image. Neural networks do that. What we see here is a PR disaster that happened to the big guys, Google, in 2015. They have an app that's called Google Photos, and you can upload photos there, and it qualifies what we see: skyscrapers, airplanes, cars, gorillas. That is a problem these days. That can't happen anymore. Why is that? Why have these two dark-skinned people been classified as gorillas? It turns out, of course, the Google engineers who trained the neural networks that were used to recognize the content of these images, they know what they were doing. They had massive amounts of training data, lots of pictures of skyscrapers, planes and whatever, lots of pictures showing faces, all of them Caucasian or Asian, none of them showing people of African heritage. Training data was biased. Here's a fun one. What do we see here? What is this? A banana. The neural network is sure that this is a banana. So with 99% degree of belief, it says this is a banana. Then there is one alternative, 1%, it could be a slug. So that's okay. It's a tolerable alternative. We can run these neural networks for image recognition sort of backwards. If you run it forwards, you feed in an image, you get out an encoding of the result, say banana. You can run that backwards, and you could say the output should be a toaster. And then you run this process backwards, like how would the ideal toaster picture look like? And this is the answer. To a neural network, that is the most prototypical toaster anyway. And of course, nobody in this room would have recognized that as a toaster up until 5 seconds ago. Now your brains cannot but see this as a toaster. Right? And once you create these images from running these things backwards, you can, insert them into real-world images using Photoshop, whatever. And what do we see in this image? Everybody in this room would say a banana and something strange. The neural network cannot but call this a toaster. There's no even like, now we have 98% degree of belief that this is a toaster, and only for 2% chance this might be a banana. So, here is where we are in 2019. Tremendous progress in AI, and mainly data-driven AI. However, there are serious problems. There's something that's called learning theory, and learning theory actually tells us, or Wapnick-Chervonenkis theory, tells us, those are mathematical results from the early 70s, that if we do statistical learning of very complicated or complex systems, and complex in terms of their degrees of freedoms or parameters that can be adjusted, there are mathematical theorems that tell us if we do that, very complicated systems, we have to use tremendous amounts of training data. And to companies like Google, Amazon and so on, that is no big deal, but to us normal people, that still is very much a challenge, and we'll see why later on. And even if you are one of these companies like Google, Amazon and so on, but your data is not perfectly representative as to what you really want to accomplish, I still run into problems. Data may be biased, for instance, lacking, not really perfect. And finally, these neural networks I've talked about, which are again the major driver of what is happening right now, are essentially black box systems. We know the mathematics they operate on, we know the mathematics to adjust them to whatever task at hand we want to solve, but once that has happened, millions of computations take place, and for the human brain it's incredibly difficult, if not impossible, to track down at which location in such a system the computation has happened that in the end was responsible for the output that was generated. These architectures are not accountable. It is hard to explain where the decisions they generate actually come from. And therefore, the take-home message is, with respect to machine learning in the year 2019, are that when we do machine learning, there is hope that we'll do tremendous things, but we need to know what we are doing. We need thick data rather than just big data. Thick data is data that is, quite a lot of volume, but also enriched with additional information with metadata. We have to make sure that when we do machine learning, we can avoid or cope with, say, bias in the data. How do we know that? Still very much an open problem to this day. And ideally, we should go for approaches whose decision-making processes are transparent, whose decisions are explainable, whose computations are accountable. And all of this then motivates the idea of thinking differently about machine learning, not just purely data-driven, but maybe trying to integrate the best of two worlds, using the knowledge in the heads of human experts to inform the learning process. So, and that explains the title of this presentation, and we start with the second half. And I am somewhat out of my depth now because the work I'm going to talk about has basically been done by my PhD students and postdocs. So let's see how we can manage here. Where are we coming from? Uwe has already said it, that for quite some time there are very fruitful cooperations between data scientists and agricultural scientists in Bonn, Jülich, Göttingen now. There's a couple of the things we have done in the past, and I thought I'd pick out one of the examples, and that is actually somewhat more in depth what Anne-Kathrin already presented when she was talking about this app that was able to identify plant diseases, especially for wheat. So we're getting a couple of pictures like these, taken out in the wild, uncontrolled conditions. So lots of spotlights, reflections, varying degrees of color saturation, whatever. We can, as the human brain is a miracle, we can easily recognize that these plants are infected by something. We can see where the infection is. It's also very easy for us to say what that is. How would we do that if we were to use a machine to do so? And again, this is pre-deep learning. This is work from 2010, 11, 12. Nobody was using deep networks back then. Nowadays people would, but I'll say why they shouldn't in a minute. Given these images, it's fairly easy. I could do this even as a non-agricultural expert to say, well, an image is, leaf is green, the infection is a hue of red. So being somewhat of an expert in signal processing, it's easy to come up with very simple filter operations that filter out the red regions in these images, and then we do some form factor analysis to get rid of these senescent parts of the plant, that you really just obtain the spots where we would say that could be a diseased spot. And then here comes the expert. I mean, this was already expert knowledge in the analysis process, right? Leaves are green, and everything that is not green probably shouldn't be there. That's expert knowledge, and we can use that to come up with computing pipelines that help us trying to analyze these things for diseases. And we end up with regions like that. And at this point, Erich Oerke from the University of Bonn told us, the data scientists who don't know anything about agriculture whatsoever, that for these parts where we recognize the presence of a disease, typically that these diseases spread in a ring-like fashion. And once we knew that, then it is extremely easy to compute rings or ring-like regions from these diseased spots, and to compute particular kind of abstract descriptions of what we see here from these ring-like regions, and to use that in a subsequent classification process. And it turns out that really worked well compared to other baselines that gave the performance boost using techniques that were en vogue back then. Again, we support vector machines. So I'll emphasize that once again. We were dealing with a problem which we could solve using machines, but human expert knowledge played a crucial role in implementing the algorithms that solved that problem. We could have done without, but that would have taken quite a while, and typically we could not have, nowadays these deep networks would, with a lot of data, probably learn by themselves that you have to analyze these spots in terms of ring-like structures. But in order to rest assured that the deep network would actually learn that, you would have to feed it with millions of examples. Right? And so therefore nowadays people are tempted to throw this hammer, this tool, onto whatever problem they have. But here this would not have made sense even if they had been available back then, because we didn't have millions of these pictures. Like how many students and PhDs did we send out in Klein-Altendorf to take pictures? We ended up with a couple of thousand of pictures, which sounds like a lot. But for statistical learning, that is nothing. And where or how are we supposed to get millions, if not billions, of annotated pictures of beet leaves? Right? Dogs and cats you get from the internet. But go to Google image search and search for beet leaves. There might be a couple of 10,000, but this is orders of magnitudes less than what deep learning would need. So that is what we did a couple of years ago, and I am extremely proud to come to what we're doing right now. I know it's very modest, I don't know, I should have mentioned it. 2 weeks ago we learned that we did win the Syngenta Challenge 2019. These are two of my colleagues. Bauckhage is one of my postdocs, and Konstantin is one of my PhD students. And a team of a couple of my postdocs and PhD students teamed up with Anne-Kathrin Marlein, and indeed they did win the Syngenta Crop Challenge 2019. So I guess that's, you know, like we should be proud. PhenoRob has won Syngenta Crop Challenge 2019. And Anna approached us in late November with the question of whether or not we should try to participate, and I was basically all in from the very beginning, because the research questions in the 2019 challenge were: can environmental data be aggregated into useful metrics presenting stress encountered by corn throughout the growing season, and can these metrics be used to discriminate between hybrids tolerant and susceptible to stresses they represent? And in the fine print beneath these questions, there was the claim that Syngenta wanted to have solutions that make sense to human experts. So purely black box neural networks would not have cut it. Because again, you don't really know what they are doing once they are trained. And what the team did, the title of the winning work is Combining Expert Knowledge and Neural Networks to Model Environmental Stresses in Agriculture. And now I'm really out of my depth, but let's try to go through what they did. The data was measurements as to weather conditions and performance or properties of corn plants, so weather, you know, daily weather. There was 2,452 corn hybrids across 1,560 locations in the US. And for each of these locations, they made daily measurements of weather conditions, 9 measurements, and features as to the behavior of the plant, 22 daily measurements. And what the team did was to design stress models for heat and drought stress, then use these models to predict yield of the plant, which was one of the features we had. And not only did they try to predict the yield based on the data that was available, but to use whatever was done during the computation as an input to a clustering system that actually was able to distinguish resilient from susceptible hybrids. So once again, there is data coming in. The total approach combines expert knowledge coming out of the brain of Anne, data-driven techniques, that's basically neural networks, and those were combined to learn to predict the yield behavior of these plants, and the information that was produced in here was also used to cluster resilient from susceptible plants. And we can't see the many arrows here, they are in light gray, but what we see is the basic processing pipeline. The general idea was to use a two-stream architecture Again, there was weather data or climate data and performance data. This data was fed into two sort of expert modules. One that learned to recognize heat stress, and the other, say, recognize drought stress. And these were neural networks. The input to these neural networks was the raw data, and derived features coming out of the brain of Anne-Catherine. So that was not just, purely data-driven, but the data was already augmented and enriched based on expert experience and knowledge. That was fed into these neural networks, who then learned to predict the yield, and in this learning process, this creates some form of very abstract representation, but that abstract representation, once again, was derived from input that was informed by human knowledge. And these abstract representations were then regressed onto yield data to predict the yield of this plant or that plant. And these abstract representations were also used in parallel in order to distinguish between resilient and susceptible plants. And this is, for instance, a picture as to how a clustering of resilient and susceptible plants would look like. And Syngenta liked that so much that that was apparently much better than what the other teams produced. And the 57.1 root mean square for yield prediction does not sound much, but this is normalized by variance in the yield data. So you would, on average, expect this to be 100%. The crazy statistics, what's going on here. This is actually very good. This is very good. So this is the lower you are beneath 100, the better you are, and this is really reliable. This can reliably predict yield expectations. And that's all. Thank you very much.